You hear about black holes and supernovas, but beneath Switzerland and France, beneath Long Island, inside metal rings the size of cities, scientists are detonating collisions hotter than any star. Temperatures hitting 4 trillion degrees, particles moving at 99.999999% light speed. Energies that rip protons apart and spit out particles that only existed 1/millionth of a second after the Big Bang. These are controlled recreations of the universe's first moments. And 7 specific collisions changed everything. Changed it so hard that physics textbooks got rewritten. These 7 moments proved quantum entanglement at energies 12 orders of magnitude higher than any lab. Proved antimatter exists in forms never detected before. Proved matter melts into a liquid hotter than the sun's core. This is documented fact from machines built by 10,000 scientists across 40 countries. And what fell out shocked everyone. 4. CERN official documentation from December 2025, and Brookhaven National Laboratory press releases from August 2024. These are peer-reviewed publications from the world's leading particle physics institutions. Now back to the information. Top quarks are the heaviest fundamental particles known. Each weighs as much as a gold atom. They live 10 to the negative 24 seconds before decay. For decades, quantum entanglement had only been seen in photons and electrons in cold, quiet labs. Nobody had proven entanglement at collision energies measured in trillions of electron volts. The Atlas collaboration changed that. They analyzed 140 inverse femtobarns of data. Roughly 1 million top quark pairs produced between 2015 and 2018. Proton beams accelerating around a 27-kilometer ring buried 175 meters underground. The beams smashed at 13 tera-electron volts. Top quarks and anti-top quarks materialized. The team selected pairs with low relative momentum. That is where spins should be maximally entangled. They measured one observable, d, from the angle between charged leptons from quark decays. For pairs with mass between 340 and 380 giga-electron volts, d measured negative 0.537. A scenario without entanglement would predict negative 0.333. The observed value set more than 5 standard deviations away. 5 sigma. Discovery. The result appeared in Nature September 18, 2024. First observation of entanglement between quarks, highest energy detection ever, 12 orders of magnitude higher than photon experiments. Andreas Höcker, Atlas spokesperson, stated the observation paves the way for investigations into quantum mechanics at previously inaccessible energy scales. CMS collaboration independently confirmed the finding. Both experiments measured the same phenomenon. Top quarks, created in Big Bang conditions, remained quantum mechanically linked. Their spins correlated through entanglement, not classical physics, at energies 1,000 billion times higher than anyone measured before. The top quark's mass and ultrafast decay made it possible. Unlike lighter quarks that bind instantly into hadrons, top quarks decay before binding. Their quantum information transfers directly to decay products. The Atlas detector weighs 7,000 tons, stands 46 meters long, 25 meters high. More than 3,000 physicists from 182 institutions built it. When top quarks decay, they produce W bosons and bottom quarks. The detector captures trajectories, energies, momenta with sub-millimeter precision. The measurement worked because quantum mechanics makes specific predictions. For entangled spins, correlation follows one distribution. Classical correlation follows a different one. The data matched quantum prediction, not classical. The gap was overwhelming. Entanglement at 13 tera-electron volts means quantum mechanics holds at energy scales approaching electroweak symmetry breaking. The standard model's quantum structure remains intact, even in conditions simulating the universe's first microsecond. Discovery confirmed, entanglement proven at the energy frontier. A new particle consistent with the Higgs boson, mass approximately 125 giga-electron volts. Statistical significance exceeding 5 sigma. This was not incremental progress. This was confirmation of a prediction made 48 years earlier. In 1964, Peter Higgs, Francois Englert, Robert Brute, and 3 other theorists independently proposed a mechanism to explain how particles acquire mass. The mechanism required a field pervading all of space. Interactions with that field would give particles mass. The field's quantum excitation, its associated particle, became known as the Higgs boson. Without it, the equations governing the weak nuclear force broke down. With it, the standard model worked. For decades, the Higgs remained theoretical. The Large Electron-Positron Collider at CERN searched through the 1990s, found nothing, but constrained the Higgs mass above 114 giga-electron volts. Fermilab's Tevatron Collider searched next, saw hints around 125 giga-electron volts, but lacked statistical power to confirm. Then came the Large Hadron Collider. Construction began 1998. Installation finished 2008. The machine cost approximately $9 billion. It comprises a 27-kilometer ring of superconducting magnets cooled to 1.9 Kelvin, colder than outer space. Proton beams circulate in opposite directions, guided by 1,232 dipole magnets, generating magnetic fields of 8.3 Tesla. The beams contain up to 2,808 bunches, each with 115 billion. Protons. Bunches cross every 25 nanoseconds at 4 interaction points. At ATLAS and CMS, the collision energy reached 7 tera-electron volts in 2011, 8 tera-electron volts in 2012. By summer 2012, ATLAS had collected 5 inverse femtobarns at 8 tera-electron volts, doubling its dataset. CMS collected similar integrated luminosity. Both collaborations searched for Higgs decays into specific channels. 2 photons, 4 leptons via Z boson pairs, tau lepton pairs, bottom quark pairs. The 2-photon channel proved crucial. The Higgs boson, if it existed at 125 giga-electron volts, would decay into 2 photons roughly 0.2% of the time. Those photons would emerge with energies and angles determined by the parent particle's mass. By reconstructing the invariant mass from photon pairs across millions of collision events, the experiments could detect a bump in the distribution. That bump would sit at the Higgs mass. Background processes also produce photon pairs, creating a smooth spectrum. The Higgs signal would appear as an excess above that background. On July 4, 2012, both teams presented their results at CERN. CMS observed a new boson with mass 125.3 plus or minus 0.6 giga-electron volts. Local significance 4.9 sigma when combining multiple channels. ATLAS observed a particle with mass 126.0 plus or minus 0.6 giga-electron volts. Local significance 5.0 sigma. Both experiments saw the same excess in the same mass region. The probability that this resulted from statistical fluctuation was less than 1 in 3 million. CERN Director General Rolf Hoyer announced, "We have observed a new particle consistent with a Higgs boson." The room erupted. Peter Higgs attended the seminar. He cried. The data came from over 300 trillion proton collisions analyzed by the LHC computing grid. Each collision produced hundreds of particles. The detectors captured trajectories, energies, particle identifications. Algorithms reconstructed which particles came from Higgs decays versus background. The 2-photon channel's signature was clean. 2 high-energy photons, nothing else. The 4-lepton channel, where the Higgs decays to 2 Z bosons, which each decay to a lepton pair, offered another clear signature. Both channels showed excess events clustering around 125 giga-electron volts. The measurement's precision came from ATLAS's electromagnetic calorimeter, which measures photon energies with resolution better than 1%, and from CMS's crystal calorimeter, 76,000 lead tungstate crystals detecting photon showers. Both detectors achieved invariant mass resolution around 1 to 2 giga-electron volts for the 2-photon channel. That resolution allowed them to distinguish the Higgs signal from background. Every prediction of the standard model had been tested except the Higgs. Now it was confirmed. The particle's properties matched predictions. Spin zero, even parity, couplings to other particles proportional to their masses. As data accumulated over subsequent years, those couplings were measured. The Higgs decays to bottom quarks, to tau leptons, to W bosons, to Z bosons, all at rates matching theory. In 2018, ATLAS confirmed Higgs decay to bottom quarks, the most common decay mode. Also in 2018, both experiments observed Higgs production in association with top quark pairs, confirming the Higgs couples to the heaviest quarks. The particle's measured mass, 125.1 giga-electron volts from combined analyses, sits uncomfortably low in some theoretical frameworks. Quantum corrections should push the Higgs mass much higher unless new physics cancels those corrections. This is called the hierarchy problem. So far, no new physics has appeared. The Higgs mass remains a puzzle, but its existence is not. Over 300 trillion collisions produced enough Higgs bosons for definitive detection. The ATLAS and CMS collaborations, totaling over 6,000 physicists, confirmed the particle's properties across multiple decay channels and production modes. On October 8, 2013, François Englert and Peter Higgs received the Nobel Prize in Physics. The citation read, "For the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron. Collider, confirmed, discovered. Mass mechanism proven, 125 giga-electron volts. July 4th, 2012, 2018. From that data, they identified 16 anti-hyperhydrogen 4 nuclei. 16. Out of billions of collisions, each anti-hyperhydrogen 4 nucleus contained 4 antimatter particles. 1 antiproton, 2 antineutrons, 1 anti-lambda. The anti-lambda is a hyperon, a baryon containing a strange quark. This made antihyperhydrogen 4 a hypernucleus and the heaviest antimatter nucleus ever detected. The relativistic heavy ion collider accelerates gold ions, atoms stripped of their electrons, to 99.995% light speed. Two beams circulate in opposite directions around a 3.8 kilometer ring. When they collide, the energy density reaches levels not seen since microseconds after the Big Bang. The ions, protons, and neutrons melt. Their constituent quarks and gluons become unbound, forming a quark-Gluon plasma. This plasma reaches temperatures of 4 trillion degrees Celsius, 250,000 times hotter than the sun's core. It exists for 10 to the negative 23 seconds before expanding and cooling. As it cools, quarks and gluons recombine into hadrons, protons, neutrons, pions, kaons, hyperons. Antimatter forms in roughly equal amounts to matter. Antihyperhydrogen 4 emerges when an antiproton, 2 antineutrons, and an antilambda happen to be produced close enough in space and momentum to bind. This is extraordinarily rare. The star detector, a house-sized cylinder weighing 1,200 tons, surrounds one of RHIC's collision points. It tracks particles using a time projection chamber, silicon vertex detectors, and time-of-flight systems. When antihyperhydrogen 4 formed, it traveled a few centimeters before decaying. The decay products were antihelium-4, itself an antimatter nucleus containing 2 antiprotons and 2 antineutrons, plus a positively charged pion. STAR had already detected antihelium-4 in 2011, setting the previous antimatter record. The new analysis used the same method. Physicists reconstructed the trajectories of antihelium-4 and pions emerging from collision debris. When two tracks intersected at a single point, a decay vertex, with characteristics matching antihyperhydrogen 4's predicted lifetime and mass, they marked it as a candidate event. Out of billions of collision events, 22 candidates appeared. Background estimation suggested 6 false positives. Subtract 6 from 22, you get 16 genuine antihyperhydrogen 4 nuclei. Statistical significance exceeded 5 sigma. The discovery confirmed several predictions. Antihyperhydrogen 4's mass matched theoretical calculations within measurement precision. Its lifetime, approximately 2.3 times 10 to the negative 10 seconds, matched the corresponding matter nucleus, hyperhydrogen 4, within experimental uncertainty. The symmetry between matter and antimatter is predicted by CPT symmetry, a fundamental principle in quantum field theory. Any violation would require rewriting physics. None was observed. The team also measured the antihypertriton, another antimatter hypernucleus, and compared its lifetime to the hypertriton. Again, no significant difference appeared. CPT symmetry held? Why is this important? The universe began with equal amounts of matter and antimatter. Today, matter dominates. Galaxies, stars, planets, everything visible is matter. Antimatter exists only briefly in high-energy events or laboratory experiments. When matter and antimatter meet, they annihilate. So where did all the antimatter go? Some asymmetry in the laws of physics must have favored matter over antimatter in the early universe. Detecting and comparing antimatter particles helps search for that asymmetry. If antimatter's properties differed even slightly from matter's, it could explain the imbalance. So far, no differences have been found. The measurements keep getting more precise. Antihyperhydrogen 4 adds another data point. Its lifetime, mass, decay channels all match expectations. The standard model survives another test, but the search continues. Future experiments at RHIC and at the Electron Ion Collider, currently under construction at Brookhaven, will produce even more antimatter nuclei. Higher statistics, better precision, deeper probes into the matter-antimatter puzzle. Liyuan Ruan, STAR co-spokesperson, stated, "It is only by chance that you have these 4 constituent particles emerge from the RHIC collisions close enough together that they can combine to form this antihypernucleus." The result was published in Nature on August 21, 2024. Heaviest antimatter nucleus, 4 antimatter particles bound together, created in a fireball hotter than the sun's core. Detected, measured, confirmed. Also, this script is researched and factual, using sources from Nature Journal published August 21st, 2024, CERN December 2025 documentation, and Scientific American published September 26th, 2024. These are peer-reviewed and official institutional sources. Now back to the information. Alice and Atlas experiments at the LHC, the first lead-lead collisions at the LHC. Center of mass energy, 2.76 tera-electron volts per nucleon pair. The results confirmed a discovery made at RHIC a decade earlier, but at significantly higher energy. The Quark-Gluon plasma, the state of matter filling the universe's first microsecond, behaves not as a gas, but as a nearly perfect liquid. This contradicted expectations. A plasma is typically a gas-like state where particles move independently, but the quark-gluon plasma flows collectively. Its viscosity is extraordinarily low, close to the theoretical minimum allowed by quantum mechanics. The measurement used elliptic flow, a hydrodynamic phenomenon. When two lead nuclei collide off-center, the overlap region is almond-shaped. Pressure gradients are stronger along the short axis than the long axis. If the quarks and gluons interact strongly, this asymmetry translates into momentum space. More particles get kicked out along the short axis. The distribution of particle momenta becomes elliptical. The degree of ellipticity, quantified by a parameter called V2, measures how strongly the system flows. Alice measured V2 for charged hadrons in lead-lead collisions. The values matched hydrodynamic models assuming a viscosity to entropy ratio near 1/4/4 pi, the lower bound predicted by string theory. This implies the quark-gluon plasma is a nearly ideal fluid. ATLAS, designed for proton collisions, also participated in heavy ion physics. ATLAS measured particle jets in lead-lead collisions. A jet is a spray of particles produced when a quark or gluon emerges from the collision with high energy. In proton-proton collisions, jets come in pairs, back-to-back, with roughly equal energies. In lead-lead collisions, one jet passes through the quark-gluon plasma, the other escapes. The jet passing through the plasma loses energy, a phenomenon called jet quenching. ATLAS observed this by measuring the energy asymmetry between jet pairs. In central collisions, where the plasma is largest and hottest, many events showed one jet with much less energy than its partner. This confirmed that the plasma is opaque to high-energy particles. The energy loss mechanisms involve gluon radiation and collisions with plasma constituents. The plasma's temperature, extracted from thermal photon emission and other observables, reached approximately 5.5 trillion Kelvin in ALICE measurements, 5.5 times 10 to the 12 Kelvin. This is 300,000 times hotter than the sun's core. At such temperatures, protons and neutrons cannot exist. Quarks and gluons roam freely, but they do not roam independently. They interact strongly. The coupling constant of the strong force, which decreases at high energy due to asymptotic freedom, remains large enough that quarks and gluons cannot be treated as free particles. They form a strongly coupled plasma, a liquid where each particle's motion is influenced by surrounding particles. The LHC's higher collision energy compared to RHIC allowed exploration of the plasma at higher temperatures and lower viscosity. The ALICE detector, specifically designed for heavy ion physics, recorded data with over 95% efficiency during the 2010 lead run. The detector includes a time projection chamber, silicon trackers, time-of-flight arrays, electromagnetic calorimeters, and muon spectrometers. It tracks thousands of particles per collision. From those tracks, physicists reconstruct the collision's geometry, temperature, pressure, and flow patterns. The results appeared in physical review letters in late 2010. Both ALICE and ATLAS papers confirmed the plasma's liquid-like behavior. The viscosity to entropy ratio remained below 1/4/4 pi, consistent with RHIC results, but now verified at nearly 14 times higher collision energy. Theorists had predicted that at higher energies, the plasma might transition to a gas-like state. It did not. The perfect liquid persisted. This discovery has implications beyond particle physics. The quark-gluon plasma's hydrodynamic properties resemble those of ultra-cold atomic gases near absolute zero, another example of a strongly coupled quantum fluid. The ADS-CFT correspondence, a theoretical framework linking gravity and higher dimensional spaces to quantum field theories, predicts a lower bound on viscosity matching the observed values. The quark-gluon plasma serves as an experimental test of these ideas. The plasma also mimics conditions inside neutron stars, where densities reach similar extremes. Understanding the plasma's equation of state helps model neutron star structure and mergers. Gravitational wave observations of neutron star collisions provide data on matter at extreme density. Combining that with LHC and RHIC data refines our picture of the strong force under pressure. The 2010 lead run at the LHC lasted 3 weeks. In that time, ALICE collected data equivalent to approximately 1 inverse microbarn of integrated luminosity. From that data set, physicists extracted measurements of particle spectra, flow coefficients, jet quenching, quarkonia suppression, and heavy flavor production. Each observable probed different aspects of the plasma. The consistency across observables confirmed the hydrodynamic picture. Quark-Gluon plasma, 4 trillion degrees. Flowing like water, measured, confirmed, perfect liquid. Most neutrino experiments use reactors, accelerators, or cosmic rays as sources. No one had detected neutrinos produced at a particle collider. The LHC produces neutrinos in abundance. Proton collisions create pions and kaons, which decay into muons and neutrinos. But those neutrinos fly in all directions, mostly undetected. The FACER experiment, installed in a tunnel 480 meters downstream from the ATLAS interaction point, aimed to catch them. FASER stands for Forward Search Experiment. It sits along the beam collision axis, where particle production is highest. The detector comprises layers of tungsten plates and emulsion films, a design inherited from neutrino detectors used in previous experiments. Emulsion films record particle tracks with micrometer resolution. When a neutrino interacts in the tungsten, it produces charged particles. Those particles leave tracks in the emulsion. By analyzing track patterns, physicists identify neutrino interactions. During LHC Run 3's pilot run in 2022, PHASER recorded data from proton collisions at 13.6 tera-electron-volts. The collaboration analyzed the emulsion films and found 8 neutrino interaction candidates, 4 electron neutrinos, 4 muon neutrinos. Statistical and systematic analyses confirmed these were genuine neutrino interactions, not background. The result, published in March 2023, marked the first detection of collider-produced neutrinos. It opened a new window. Collider neutrinos have higher energies and different flavor compositions than those from other sources. They probe the weak interaction in a regime not accessed by atmospheric or solar neutrinos. PHASER's success also demonstrated the feasibility of forward physics at the LHC. The experiment, small and relatively inexpensive compared to the main detectors, occupied a previously unused tunnel. Its discovery potential extends beyond neutrinos. PHASER searches for long-lived particles predicted by theories beyond the Standard Model, particles that travel hundreds of meters before decaying. None have been found yet, but the detector keeps running. Upgraded for Run 3, PHASER now includes a spectrometer and a dedicated neutrino subdetector. It aims to detect thousands of neutrinos over the coming years. That dataset will allow precision measurements of neutrino cross-sections and searches for new physics in the neutrino sector. Detecting 8 neutrinos might sound modest, but collider neutrinos had never been seen. The experiment proved the concept. Neutrinos from proton collisions, detected, measured, confirmed, 380 giga-electron-volts. The observable D measured negative 0.52, more than 3 standard deviations from the no entanglement scenario. This preliminary result, presented at conferences and posted to arXiv in November 2023, spurred intense activity. The CMS collaboration launched its own analysis. Theorists refined predictions. Experimentalists improved systematics. By September 2024, Atlas published the definitive measurement in Nature. CMS confirmed it independently. The 2023 result was significant because it identified the optimal kinematic region. Top quark pairs produced near threshold, where their relative momentum is low, exhibit maximal entanglement. Away from threshold, entanglement weakens. Classical correlations dominate. The Atlas analysis divided the data into bins of top pair invariant mass. For each bin, they calculated D. The strongest entanglement appeared in the 340 to 380 giga-electron-volt bin, exactly as theory predicted. This threshold production occurs when the collision energy barely suffices to create both quarks. They emerge moving slowly relative to each other. Their spins remain correlated by the production mechanism. In higher mass bins, the quarks receive large boosts, reducing entanglement. The measurement technique relied on angular observables. The angle between the two charged leptons from top quark decays, measured in the top and anti-top rest frames, encodes spin information. That information translates into the D parameter. Positive D indicates classical correlation. Negative D below negative 1/3 indicates entanglement. The observed value, negative 0.52, sat deep in the entanglement region. Statistical uncertainties were small due to the large data set. Systematic uncertainties from detector resolution and background modeling contributed more. But even with systematics, the significance exceeded 3 sigma in the 2023 analysis and 5 sigma in the 2024 analysis. The result, bridged particle physics and quantum information science. Entanglement, typically studied with photons in tabletop experiments, now appeared in collider data. The top quark, heaviest of all particles, served as a probe of quantum mechanics at the energy frontier. Future measurements could test entanglement in other systems, W boson pairs, Higgs boson pairs. Even gluons, the carriers of the strong force, might exhibit entanglement under the right conditions. Theorists are developing frameworks to measure entanglement in jets, which are macroscopic objects containing thousands of particles. If entanglement persists in jets, it would demonstrate quantum effects at scales far beyond individual particles. The Atlas 2023 result hinted at this new frontier. The 2024 publication confirmed it. Top quark entanglement, measured at threshold. Quantum mechanics holding at 13 tera-electron-volts, confirmed. This nucleus contains 2 antiprotons, 1 antineutron, and 1 antilambda. It is the heaviest antimatter hypernucleus detected at the LHC. The measurement used lead collision data from 2018, recorded at 5.02 tera-electron volts per nucleon pair. Alice employed a machine learning technique to identify hypernuclei and anti-hypernuclei among collision debris. Traditional search methods rely on reconstructing decay vertices and invariant masses manually. Machine learning automates this process, scanning millions of event topologies for patterns consistent with hypernuclei signatures. The algorithm was trained on simulated data and validated on known hypernuclei. Then it searched the 2018 dataset for hyperhydrogen-4, hyperhelium-4, and their antimatter counterparts. The result? First evidence of anti-hyperhelium-4 with a significance of 3.5 standard deviations. This fell short of the 5 sigma discovery threshold, but constituted strong evidence. The collaboration measured the mass and production yield of anti-hyperhelium-4. Both matched expectations within uncertainties. The mass agreed with theoretical predictions based on nuclear binding energies. The production yield matched statistical hadronization models, which predict how quarks and gluons from the plasma recombine into nuclei. Alice also measured the antiparticle to particle yield ratio. For both hypernuclei studied, the ratio agreed with unity. This means matter and antimatter were produced in equal amounts, consistent with CPT symmetry. At LHC energies, no asymmetry appears. The matter-antimatter imbalance in the universe must arise from other mechanisms, likely involving processes in the first seconds after the Big Bang that are not replicated in colliders. The Alice detector recorded 2.0 inverse nanobarns of integrated luminosity during the 2018 lead run. That corresponds to approximately 600 million collisions. From those collisions, the machine learning algorithm identified a handful of anti-hyperhelium-4 candidates. Each candidate required the anti-lambda to decay into an antiproton and a positively charged pion, then the remaining anti-helium-4 nucleus to be detected and identified by its energy loss in the detector's tracking systems. The Alice time projection chamber measures ionization energy loss, which varies with particle type and velocity. By combining energy loss with momentum and time of flight information, the detector distinguishes antiprotons from pions, antideuterons from antihelium, and so on. The machine learning approach outperformed conventional methods because it could handle the complexity of hypernuclei decays without requiring physicists to manually define all possible signatures. The algorithm learned the patterns from simulated data and applied them to real data. This technique will become standard in future heavy ion experiments, where data volumes exceed human capacity to analyze. The Alice collaboration continues to collect data during LHC Run 3. With upgraded detectors and higher luminosity, they expect to observe anti-hyperhelium-4 with discovery-level significance and measure other exotic nuclei, including hyperhelium-5 and beyond. Each new nucleus provides a test of nuclear forces and symmetry principles. The discovery also connects to dark matter searches. Some theories predict dark matter interacts with ordinary matter through processes that produce anti-nuclei. Cosmic ray experiments search for anti-helium nuclei in space. Detection of even a single anti-helium-4 nucleus in cosmic rays would be a smoking gun for dark matter annihilation or other new physics. Alice's measurement of anti-hyperhelium-4 production rates in collisions helps interpret those searches. If you know how much anti-hyperhelium-4 is produced in high-energy collisions, you can estimate the background from cosmic ray interactions. Any excess would point to new sources. Anti-hyperhelium-4, 2 antiprotons, 1 antineutron, 1 anti-lambda, detected at the LHC. First evidence, December 2024. Machine learning enabled, confirmed. The Large Hadron Collider cost $9 billion to build. It operates at a budget of approximately $1 billion per year. The experiments, Atlas, CMS, Alice, LHCb, each cost hundreds of millions to construct. The relativistic heavy ion collider, operational since 2000, represents a similar investment. These machines are humanity's most complex tools. The LHC's superconducting magnets, cooled to 1.9 Kelvin, generate fields stronger than Earth's magnetic field by a factor of 200,000. The cryogenic system uses 96 tons of liquid helium. The vacuum inside the beam pipes is 10 times emptier than outer space. Proton bunches circulate at 99.9999991% light speed, 11,245 laps per second. When they collide, the energy density exceeds anything in the universe except black hole horizons and the Big Bang's first moments. Detectors surrounding the collision points are engineering marvels. Atlas weighs 7,000 tons, CMS 12,500 tons. Alice, designed for heavy ions, records up to 2,000 particles per collision. These detectors capture particle trajectories with micrometer precision, measure energies with percent level accuracy, identify particle types by ionization, time of flight, and calorimetry. Data flows at rates measured in petabytes per year. The worldwide LHC computing grid processes it, distributing tasks across 170 computing centers. Machine learning algorithms, trained on simulated collisions, filter signal from noise. The searches require patience. The Higgs discovery came after analyzing 300 trillion collisions. Anti-hyperhydrogen 4 appeared 16 times in 6.6 billion events. Top quark entanglement demanded 140 inverse femtobarns, roughly 50 million billion collisions. Most collisions produce nothing interesting. Background overwhelms signal, but with enough data, rare processes emerge. And when they do, they redefine reality. Quantum mechanics operates at the highest energies. The standard model remains unbroken. Antimatter obeys the same laws as matter. The universe's first microsecond can be recreated in a laboratory. These are not abstract truths. They are facts extracted from collisions, measured by detectors, analyzed by physicists, published in peer-reviewed journals. The sources are clear. Nature, September 18, 2024, reports quantum entanglement in top quarks. Nature, July 2012, and subsequent reviews documents the Higgs discovery. Nature, August 21, 2024, announces anti-hyperhydrogen 4. Physical review, letters and CERN press releases from November 2010 detail the Quark-Gluon plasma's liquid behavior. March 2023. FACER results, published in peer-reviewed outlets, confirm collider neutrinos. Alice's December 2024 preprint on Archive describes anti-hyperhelium 4. These are original research papers from the ATLAS, CMS, ALICE, STAR, and FASER collaborations, institutional publications from CERN and Brookhaven, and reports in Nature, Physical Review Letters, and Scientific American. No speculation, no exaggeration. Documented fact. After 2025, the LHC shuts down for upgrades. The high luminosity LHC, scheduled for 2030, will deliver 5 times more collisions per year. Detectors will be upgraded. The physics program extends into the 2040s. Meanwhile, plans for future colliders advance. The Future Circular Collider, proposed by CERN, would be a 100-kilometer ring producing collisions at 100 tera electron volts, 7 times the LHC's energy. Cost estimates range up to $20 billion. Approval is expected by 2028. If built, it would operate into the 2070s. China proposes the Circular Electron-Positron Collider, followed by a Hadron Collider stage. Japan considers the International Linear Collider. The United States plans the Electron-Ion Collider at Brookhaven, scheduled to begin operation in the 2030s. Each machine targets different physics. Electron-positron colliders produce clean environments for precision measurements. Electron-ion colliders probe the structure of protons and nuclei. Hadron colliders reach the highest energies, accessing heavy particles and rare processes. Together, these facilities will map the energy frontier. The collisions documented here, the 7 that rewrote physics, represent the foundation. Entanglement at 13 tera electron volts sets a baseline. The Higgs discovery confirmed the mass generation mechanism. Anti-hyperhydrogen 4 and anti-hyperhelium 4. Constrained matter-antimatter asymmetry. Quark-Gluon plasma reveals the strong force under extreme conditions. Collider neutrinos open forward physics. Each result answered questions and raised new ones. Quantum mechanics holds at high energy, but why? The Higgs mass is 125 giga-electron volts, but why so light? Antimatter and matter are symmetric, but why does matter dominate the universe? The Quark-Gluon plasma flows like a liquid, but what is its viscosity's precise value and temperature dependence? Neutrinos are detected from colliders, but what are their exact properties, and do they exhibit new interactions? These questions drive the next generation of experiments. The answers will come from more collisions, better detectors, deeper analyses. The process is iterative. Build a machine, collect data, analyze, publish, build a better machine. Repeat. This is how particle physics advances, not by sudden revelations, but by accumulating evidence. Each collision adds a data point. Each data point refines a parameter. Each parameter tests a theory. Over decades, the picture clarifies. The standard model, formulated in the 1960s and 70s, has survived every test. Thousands of measurements across energy scales from MeV to TeV agree with its predictions. Quantum electrodynamics predicts the electron's magnetic moment to 10 decimal places. Experiment matches. The weak mixing angle, measured in neutrino scattering, Z-boson decays, and forward-backward asymmetries, agrees across experiments. The strong coupling constant, extracted from jet rates, heavy quarkonia, and lattice QCD, converges. The Higgs couplings, measured in multiple channels, align with predictions. No significant deviations appear, yet the standard model is incomplete. It does not explain gravity. It does not include dark matter. It does not explain the matter-antimatter asymmetry, neutrino masses, or the hierarchy problem. Extensions to the standard model, such as supersymmetry, extra dimensions, or compositeness, could address these issues, but none have been confirmed. The LHC has searched for supersymmetric particles up to masses of several tera electron volts. Nothing. Searches for extra dimensions, black hole production, leptoquarks, heavy neutrinos also came up empty. Either new physics is heavier than current colliders can reach, or it hides in rare processes not yet observed, or it does not exist in the forms predicted. The discoveries documented here do not extend the standard model. They confirm it. Entanglement, as predicted by quantum mechanics. The Higgs, as predicted by the BEH mechanism. Antimatter, as predicted by CPT symmetry. Quark-Gluon plasma, as predicted by QCD. Neutrinos, as predicted by weak interactions. Every prediction held. This is not failure, this is success. The theory works. But the mystery remains. Why this theory? Why these particles, these forces, these parameters? The collisions provide data. The data constrain theories. The theories guide experiments. The cycle continues. 103 nuclei during the late 2010s by inducing photon swaps in near-miss collisions of lead 208 nuclei. This was not a collision in the traditional sense. The lead nuclei passed within femtometers of each other without touching. Their electromagnetic fields, equivalent to intense pulses of light, interacted. Virtual photons from one nucleus struck the other, knocking out neutrons. The result? Transmutation of lead 208 into gold 203. This represents the first photoproduction of gold nuclei in a collider. The process mimics nuclear reactions in stars, but occurs in a controlled laboratory setting. 260 billion nuclei, while sounding large, weigh approximately 90 picograms. Barely anything. But the physics is profound. High-energy photons, generated by accelerated heavy ions, can induce nuclear reactions. This opens a window into photonuclear physics, relevant for understanding stellar nucleosynthesis and cosmic ray interactions. It also demonstrates that colliders are not just tools for particle physics. They are nuclear reactors, alchemy machines, recreating processes that occur in the cosmos, lead into gold, not by mysticism, but by electromagnetic fields. Documented, measured, confirmed. This is the power of particle accelerators, not just to discover new particles, but to recreate the universe's most extreme conditions, to test theories, to measure constants, to push the boundaries of human knowledge. 7 collisions rewrote physics, 7 moments where data exceeded expectations, where signals emerged from noise, where predictions became reality. Quantum entanglement at the energy frontier. The Higgs boson completing the standard model. The heaviest antimatter nuclei ever detected. Quark-Gluon plasma flowing as a perfect liquid. Neutrinos from a collider. Each result required precision, patience, and the collaboration of thousands. Each result stands as a testament to what science achieves when humanity coordinates effort and resources toward understanding the fundamental nature of reality. The universe operates by rules. Particle colliders reveal those rules, collision by collision, measurement by measurement, discovery by discovery. This is physics, documented, proven, confirmed.